again, let's look at the big theme. The theme is the following: we want to study the brain, and we want to study it in the lens, the perspective of mathematics. You know, and so that's great that we want to do that. And what I need to tell you is, eventually, when we actually tell you how this works, how we look at a neuron and how we might study it, it's going to turn out that we need to solve differential equations. Most of the basic models, as I've written here, of these neuron models or ways of trying to study the brain, the language of the equations, the type of equations that are good models, turn out to be differential equations. And so that means we have to be able to solve them if we want to get any information. And the downside to that is that even though in a calculus course and in a differential equations course you might study how to solve them by hand, it is more often than not that you can't solve them by hand. You can't just do a bunch of computation and get the answer. What often happens is we have to rely on deep theory. We have to rely on the fact that the solution exists, and then we have to go to a computer and approximate. And so that's what this first homework is about. This first homework is about getting you guys to understand that we can't, even if, you know, I shouldn't say we can't, but oftentimes we can't. So the first homework, we're giving you 6 equations. These are ones that you can solve symbolically. But then I also want you to solve them using Euler's method. And then when you do that, you can see how the approximated solution actually approximates the actual solution. So let's do an example, and we'll steal one right from the homework, and we'll get you started. So I have the equation dy dt equals yt. And I have the initial condition that the solution I want is the one that passes through the point 0, 1. So we're going to solve this 2 ways. So the first thing we'll do is we'll solve it exactly, and then we'll approximate solution using Euler. All right. So hopefully does everybody understand what we're going to do? We're going to do it twice, 2 different ways. Now, what I need you to understand is, if you look at this equation is a special type. It's what we call a separable equation. You learned about these in Calculus 2, and I think Zaishan, you and Jingji should have seen this in differential equations class for sure. Yep. And so it's worth solving it anyhow, even if you've seen it. So let's do the exact solution. So since it's separable, let's see if we remember this. You're going to write this as 1 over y dy equals t dt. So this was the symbolic strategy that worked. So again, I'm separating my variables. My dependent variable is y. My independent variable is t. So that means I'm going to write this as 1 over y dy. Integral has to be equal to integral t dt. And these are both elementary integrals. This is log y equals 1/2 t squared plus c. And then if I get rid of the log, I am left with y equals e raised to the 1/2 t squared plus c. And you guys might remember that we often abbreviate this, or rewrite it, I should say, is ae to the 1/2 t squared. So,
Dr. Grady,
yes.
I forgot how did you get 1 over y?
So if you go back to the previous page, I'm just taking the y on the right-hand side of the equation, and I'm dividing it to the other side. So you might, the proper way of saying this is that I am dividing both sides of the equation by y. I think sometimes in school you're taught that's called like cross multiplying or something like that.
Oh, yes. Okay, now I remember it.
So if we assume that y is not 0, then that's legal to do.
Okay.
And just take the integrals and then we solve for y. So now we have a perfectly nice function. And if you wanted to, you could differentiate this and you would see that it's true for all a. Any a you pick any number you want, put it in for a. This is a solution. So cool. Okay, so we want a specific solution. So you guys might remember this is called, because it depends on a, this is called the general solution.
Mm-hmm.
And we're not interested in the general solution per se, because we're told, if you look at the problem, we want this particular solution, the one that satisfies y of 0 equals 1. So what we want is so what we do is we quote unquote plug in and solve for the value a. So what is y of 0? Well, y of 0 can equal two things. On one hand, y of 0 by definition equals a e to the 0, which is a. And y of 0, we also want it to be 1. So what does this line of reasoning tell us? This tells us that the a we seek, the one we need, is a equals 1. So our particular solution is y of t equals e to the 1/2 t squared. That is the guy that we're after. That is the solution to our problem. Does anybody have a question about this? So what we often call this is we call this an analytic solution. We use symbolic manipulation, deductive reasoning, calculus, etc., to reason that if to be a solution of that equation, you have to be this function. This is the only solution to that equation. Now, Jingzi and Zayshin, you might remember in differential equations, you probably stated this theorem called the existence and uniqueness theorem.
Mm-hmm.
So there's this big theorem that you study in a math class, that type of math class. It says if there's a solution, it's unique. So this is the only solution to the problem that we stated. Now, because there's this, what we call a uniqueness or existence theorem, we now know that even if we couldn't solve this by hand, we do know if we tried to approximate it, we could analyze how good our approximation is. So that's what we're going to do next. Does anybody have a question about this? All right, so now we want to solve it in an approximate form. And what I'd like to do at the end is I'm going to show you, we're going to do it by hand at first. But then what I'm going to do is I'm going to show you how to do this on using some programming. And hopefully you guys will take the time to learn it. As I said, one of the big goals you should have for yourself in this summer course is at the end of the semester, you should be able to solve differential equations on a computer. That's a great skill to have when you go to, what's that?
Yeah, I know.
So that is the skill you guys want to have when you go on job interviews and internship interviews. You want to say, hey, look what I can do. Because that's the kind of stuff we do in the real world. I shouldn't say we do, I guess we do. That's one of the skills you want to have. It's a great skill to have. It's used in many areas of science and engineering and obviously programming stuff. Okay, so we're going to do that now. So now we're going to solve. And I'll put solve in quotations because we're really approximating it. So, okay, so let's remind ourselves of what the equation is. Our equation was dy dt, and it was equal to y of t, and then our initial condition was y of 0 equals 1. Now, what's very smart to do and what's very useful is to give the right-hand side of our equation a name. And so if you remember what we gave this thing a name last week, I think I called it capital F or maybe capital G, I forget. I'm going to call this thing f of y comma t, because that's what it is. It's an expression that is dependent on y, and it's an expression that depends on t. So it's real useful to do this, to give it a name. So that's what I'm going to call this. Does anybody have a question about this? Okay, now what we're going to do is we are going to approximate a solution a certain way. And the algorithm that's called Euler's method starts as follows. Don't also forget we give this guy a name. We'll call this guy y sub 0. That's the name we give this creature. And now what we're going to do is we're going to construct a sequence of y values. Hold on one second. You're all right, Rick. All right. So again, the first thing you want to do is you need to recognize what your your function is. And in this case, I'm calling it f of y comma t because it depends on y and it depends on t. Okay, so what do we have to do first? If we want to use Euler's method, the first thing we need to do is we need to decide on what we call the step number. So what I'll do is I'll choose h equals 0.1. Okay, now here's what we're going to do. We're going to construct a list of y values, our approximate y values. So these guys, so let's think about what we know. We know so we're going to so these guys, their goal of these guys is to approximate the actual solution in the following way. So I'm going to construct y sub 2 by saying that it's y sub 1, which I already have. Or excuse me, let me slow down. I skipped a step. This would be y sub 1.
Dr. Grady,
Yes.
can you back to the previous slides, please?
Sure can. Give me 1 second.
Yeah, no problem.
This slide?
Yes, yes. I have a question. You say you will choose h equal 0.1?
Yeah.
Okay, okay. Yeah.
So that you get to decide what value of h do you want. You could choose any value of h. I mean, you want it to be a small number. The smaller h is, the more accurate your approximation should be.
Okay, so I can put like 0.1 or 0.001 or something like that.
Absolutely, right.
Okay, yeah, okay. Now I good.
Does that make sense?
Yes, yes.
All right. Now, so if we go back here, let me clean this up a little bit. So I guess I should have been, if I go back one screen, maybe I should have been a little more clear. We also want to give this number right here, we're going to call our t sub 0, our first time. And we have to think about, remember, what we're really doing is we're taking our domain and we're partitioning it into a discrete number of values. The first one is t sub 0, then it's t sub 1, t sub 2, t sub 3. So let me be real clear what I mean by that over here. So I call this h, and then this is, I want to get I don't want to make a mistake. Get ahead of myself, and then you guys will be very confused. I don't want that. So then this is going to be h times f. And then the first thing I'm going to do, remember, what was my f? It was y. So I call this y comma t. So I'm going to put my first y value in. That's my y of 0. And then my first t value in, which is t of 0. And then how do I get my second approximation? I plug in as follows. And this pattern goes forever and ever. And for those of you who don't remember, how am I getting these t's? Well, what is this might not be clear. You might not remember this exactly. So let me be very clear. Where are these t's coming from? Well, t of 0 is equal to 0 because that's the initial time on our problem. T sub 1 is going to be 0 plus h. T sub 2 is going to be 0 plus 2h, etc. So in general, what is the nth time, or the nth point? So this would be t sub n plus 1 is always, if you want a general formula, it's always your previous chi plus your step size. Okay, so does this make any sense at all? Does anybody need something clarified?
I have a question.
Yes.
For T2, why is it 0 plus 2h and not T1
Well,
plus?
okay, yeah, I could do it. Well, it's not wrong either way, but I agree with you're saying. It would have been better to, I agree with you. Let me write this cleaner. You're right. What this should be, so that so you can think about it for any example, not just this one. It's this. Is that more clear?
Yep.
Yep. But in this case, yeah, you're right. So I should have been more clear with that. Okay, so what I'd like to do now is I'd like to use a calculator or anything. I'm just going to make a table. Now we're doing this the long way right now. You should do this once by hand with like a handheld calculator just to see you get the gist of it. And then we'll graph it, and then we'll move on to show you how to do it more efficiently. Any other questions before we do that? All right, so let's make a table. So here's one way I like to do it. I like to list my values of n. So we start, and then we have our values of t, and then we have our y sub n. And then it's also nice to get your actual value. Your actual would be y evaluated at t sub n. So this would be your actual values. So let's say we're going to start with, so 1, 2, 3, 4, 5, 6. It's got the 7 for now. So this is 0, and then this is h, and then this is going to be 2h, etc. So we can actually put the number in. And if at any moment you need something clarified, please don't hesitate to ask. So don't forget our main formula. Our main formula is that y sub n plus 1 is y sub n plus h times f evaluated at y sub n comma t sub n. So we already know what y of 0 is. That's the guy we started with. That's 1. And of course, our actual value, that's what we're going to get. We're going to get that. So we agree completely right here. Now, what I'm going to do before I go to do this is I'm going to open up a calculator. Maybe I'll use Desmos. Let me show you what I'm going to do. So what I'm going to do is I'm going to share this. Let me share this with you. So on Desmos, I'm just going to type my solution. And what was my solution? It was y equals e raised to the 1/2 t squared. I'm going to write x squared, though, just because Desmos likes x's better than t's. So I can make a little table of my exact values using Desmos. So the first thing, if I plug in 0, of course, we get 1. Now, if I plug in 0.1, what do I get? I get that number. So then if I plug in 0.2, I get that. 0.3, 0.4, 0.5, 0.6. I think I went up to 7, right? So I'm just getting, these are the exact solutions. Does anybody have a question about this? And why am I doing this again? I don't have to do this. I'm just doing it to put it in my little table. So I have this table. So this is 1.005, and then this is 1.0202 if I round. 1.046. 1.0832. 1.1331, and then 1.9197, and then 1.277. So those are my quote unquote exact values, or the actual values of the solution. Now what I want to do in the third column is these are going to be my approximated values. So how am I going to get them? Well, I'm going to get them using the formula. What is, for example, what is y of 1? Well, y sub 1 is 1 plus 0.1, because that's h, times f of this, which would be f of y sub 0 comma t sub 0, which is 1 plus 0.1. And then what are you plugging in here? You're plugging in, this is y times t, so this becomes times y sub 0 times t sub 0. But t sub 0 is 0, so this goes away, and you get 1. So make sure you understand how I got that. So I get 1 again. Then what's y sub 2? Y sub 2 would be 1 plus 0.1 times f evaluated at, well, it's going to be y sub 1 t sub 1, which is y sub 1 is 1, and then this is 0.1. So this is 1 plus 0.1 times 0.1 times 1, which if you go to a calculator, you get 1.01. Does anybody have a question about this? Comments, concerns? So you can see this is quite tedious to do by hand. Does anybody have a question, comment?
We can just use a like for loop to do it on the
Oh,
coding.
absolutely. That's exactly what I'm going to tell you in a second.
Oh, okay.
Yeah,
That'll be a lot easier.
Yeah, well, absolutely. But like I said earlier, I would never encourage you to do it this way all the time. What I would encourage you to do is when you're learning it. Now,
okay.
everybody in this class is at a different level of how comfortable they are with this crap.
Mm-hmm.
But when you're learning it, it is never a bad idea to do it like this once or twice. And then you're correct. At the other scheme of it, you want to be able to use technology. I mean, look, you can go to a computer and do Euler's method in no time. Excuse me. There's free. Oh, I just Googled it right here. Yeah. So I just Googled Euler's method calculator, and there's a web page that does it. That does all it for you. But look, the important thing for you guys isn't solving these for homework. The important thing is that you actually learn it so you can use these skills to do other things. I mean, the reason we teach Euler's method in classes like this is because it's one of the most basic ways of learning how to run a for loop if you want it. Or if you get a little more sophisticated, you can run a while loop, and you can go until you get any degree of accuracy you want. Does that make sense? So if you know anything about a while loop, there you go. But yeah, it's not hard to do this, and you could even find websites that'll show you the exact solutions versus these guys anyhow. So let's see if I'm on a web page now. I wonder if it's going to work for me. I think it will. Let's see if I can get this to work. This web page looks promising. If it works, I'll show you it. It's not working. What is happening? It's not working. I can't get this particular one to work. Why isn't it working? Anyhow, you can definitely find calculators out here that'll do this for you. But again, what I would highly encourage you do is that you learn how to do this. You learn how to do this on your own and use it as a way to teach you how to write simple code. Does anybody have a question about that? Hold on. Bear with me. I found this one. This looks like a very useful graph. Yeah. So I found this web page. And again, I would highly encourage that you check things out. Here's one. It's an Euler method, and it spits out the data. You'll see it spits out the numbers we found: 1, 1, 1.01, 1.030. So it'll do it for you. Does anybody have a question about this? Again, the only way you're going to learn this is if you continually do it over and over again. I mean, just for fun, let's just make sure we get the next one to be correct. What would, if I want to get y sub 3, well, then I'm plugging in y sub 2, which is 1.001. You can actually do this if you wanted. You can actually do it on a you can use Desmos to do it, or GeoGebra. There's lots of ways to do this. But as I said, the simplest way, once you teach yourself how to do it, is to use some sort of computational package. I use what's called Octave. By the way, I bet you, even if we went to our great friend Wolfram, I'm sure it'll do it there too. Let's see, I click on it. Yep, it has it. It'll do it for you on Wolfram. So there's lots of places that you can see how to do it, but I would highly encourage you to learn how to do it on yourself, on your own. Does anybody have a question right now about what we mean by this? And by the way, if I go back to Desmos and I zoom in a little bit on this thing. So if what I want to show you, let me go to share. If I go back to Desmos, let me plot. You can plot your actual, and I just lost it. Why did it disappear? Oh, boo. My whiteboard, I can plot these solutions. It's 1, 1. So let me sort of show you what I'm saying here. So I'm going to type a couple things in here. So if I go and share this Desmos thing, so let me change the colors here. Let's make these all purple. So what I've done is the red curve is the actual solution that we solved, that e to the 1/2 2t. But what you'll notice is if I plot my approximated values, you'll see that they start off good, but then they start to separate away, as you would imagine, because at each step we're increasing our error because we're compounding error. And if you drew a polygonal line through these solutions, that's what we mean by an approximate solution. So again, if I zoom in a little bit, you would imagine that if I drew the line from here to here and then here to here, I'm getting an approximate solution. Does anybody have any comments or questions about that? Okay, now, sweet. So now what I want to do is I want to show you something on what's called Octave. I would highly encourage you download Octave if you don't have it. It's free and it's good to do computational stuff. It's a good way to learn different methods of coding, and this is what I use. So any code that I share with you, if you already have Octave, you can just modify what I give you. Okay, so does anybody have any questions before I show you this stuff? Okay, good. So I'm going to share this with you, and it's going to be pretty cool. Here we go. This is one way of doing, of writing code to do this. So there's going to be a learning curve for some of you before I show you this. You can't let it let it deter you, especially for those of you who aren't familiar with this kind of stuff. What I'm going to do is I'm going to have a computer just do all that work that I just did, and it'll do it in a second. And then I'm going to I'll post this code to Canvas so you guys can check it out later on. Okay. So let me share it with you. So what you should see now is a screen that says at the top, you'll see F Euler .m. That's the name of the file. So the file extension for all these are .m. If you've ever worked with MATLAB, they're the same type of files. And you'll see that I'm sort of commenting out everything that's green, everything that has that percentage sign is not read by the computer. That is only read by you, the user. And so what I like to do is I like to set a timer. To set a timer, you put TIC at the top and then TOC at the end. And what it does is, this is very useful later on to tell you how long it's going to run to do all the computations. And you'll see that I need to define my function. So one of the ways we can define a function in Octave or in MATLAB is like this. Here's my F. I have to give it this command, this inline business. That's just what it does. And then you'll notice I have a comma, and after the comma, I give you what are the variables of my function. My variables are y and t. And now let's say we want to compute 10 values. So I'm going to modify. This is for an old function. So let's say we're going to do 10 computations. And let's call this h, since that's what we were calling it, not dt. H, we'll say 0.1 like we did before. So right now I'm telling the computer exactly how many times I want it to do a computation. Do I want to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to increase at each step 0.1. That's what we said. Now, a good habit I like to get into is I like to set aside storage for the computer. I like to say, and this is going to be maybe a little tough for maybe you, Abdul. I'm not quite sure how much familiar you are with what a vector is. Maybe you are, maybe you aren't. But what Octave and MATLAB like to do is they like to store everything in vectors. It actually makes things very easy. So I'm going to store my T0, my T1, my T2, etc. I'm going to put that list in a vector, and I'm going to call it T. And then I'm going to call Y. Y is going to be the vector of all my approximated values. So notice what I'm doing is I'm saying, here's a vector. Right now, everything is 0 in that vector. And then I'm going to replace 0 with whatever values the computer gets for me. And so what is my initial value? Well, my initial time, my first time is 1. Now look, computers don't do subscripts. So instead of using subscripts, I'm using parentheses. So this right here, this would be your, this is going to be very scary, but it's kind of confusing. This is my t of 0. Oh, excuse me, I lied. That's not t of 0. This is my t sub 0. And then what was my first value of y? My first value of y is 1. So this is my y sub 0. Now this is kind of confusing at first because you guys are saying, well, I thought that y of 0 was y sub 0. Yeah, it is, but the computer doesn't let us do that. The computer says we can start at 1. We can't start at 0. So that's sort of, again, that's one of the learning curves. And now what I'm going to do is I'm going to have the computer compute my values. Look at the formula I have here in yellow and green. I'm using I instead of N, but you get the idea. And so this is one way to do Euler's method. I'm not saying this is the best way to program it. You might have a better way. You might go to Stack Exchange, or you might find on the internet someone else's code that you like better, or you learn, understand it better. But for me, this is how I think was best for me to learn. I just have to make sure I do everything right. So you can see what I'm going to do is I'm going to compute my y's and then I'm going to compute my t's. This is just one way of doing it. And then what I like to do is I like to, when I'm first learning it, I like to use this thing I call check 1 and check 2. I like to make sure that I've programmed things correctly. So before I run any of this, let me comment this out for a second. What I'd like to do is I want to run this code, and I want to make sure that it gives me the values I expect. So when I have this check 1 equals t apostrophe, check 2 equals y apostrophe, what that apostrophe does is that takes our vector, our list that's horizontal, and it transposes it so that it's vertical, so it's a little easier to read. So what I'm going to do is I'm going to run this. And by the way, for those of you who aren't familiar with this stuff, you have to first save it. And the file name, if you look in the top right, the file name has to be .m. And once it's saved, once you click this gear with this arrow in it, it'll run it. And right now it doesn't look like anything happened because I'm in what's called the editor. But if I go to the command window, you'll see that it spit things out. Now look, here's my check. My check is my time values, my t's, t sub 0, t sub 1, t sub 2, 3, 4, 5. You'll notice those were the values we had in our table. And then you'll notice this value these are my y values. Remember, we calculated the first 3, 1, 1, and 1.01. And then it calculated the 4th, the 5th, the 6th, the 7th, the 8th, blah, blah, blah. Does that make sense? So those are what we did by hand. That was the computer. It did it in 0.029 seconds. So these numbers are what I expect. So I think that my code is correct. Now I want to make everything pretty. So what I'd like to do is I would like to plot my solution and compare it with the regular solution. So how did you plot when you were first a kid? Well, when you were first a kid, you had to give it x values and then y values, and you connected the dots. Well, that's exactly how the computer graphs. So what I want to do is I want to tell it what numbers to graph. I have those here. Those are the domain. And then my exact solution, we found the exact solution. What was it? Well, the exact solution to this particular problem was e raised to the 1/2 times our input, which in this particular case is t1 squared. And what I'm going to do is I'm going to have the computer graph my approximated solution and my actual solution. So there's going to be a learning curve for you guys with this. And that's part of the reason that you'll notice that I have this period here before my exponent, my raising of the power. So that's something. So the computer has built-in code that says if you multiply something, how do you multiply it? Now this is very unique and new to those of us who haven't seen this before. So if you look at t sub 1, the way I'm defining t sub 1, I'm defining it as what's called a vector. It has so many entries in it. And so what allows MATLAB or what allows Octave or Python or whatever, you know, computational package you're using, what allows it to do arithmetic quickly is it's using vectors. And so when I do that t1, that's a new variable. This might be very, you know, as I said, there's going to be a learning curve for some of you here. I am saying take that vector t1 and that dot caret, that means square each entry in it. That's what that means. And so what happens when I run this code is you're going to see a picture. After it fixes from, oh, now it's not responding. Maybe we won't see a picture. My computer might be exploding. Uh-oh, I messed. We might have to go find out where the air is. This is learning on the fly. I don't know what's happening here. We're not responding. Can you imagine? What do you guys see right now? Do you see my windows?
Yeah. That's the screen.
What in the heck just happened? Oh, there it is. Sweet. So there we go. Now, do you guys see this picture? Maybe I should change the, so you should see figure 1. Does everybody see figure 1? And you have a blue curve. That is our exact solution.
I don't see any figures.
Oh my Lord, you don't see anything. Let's go see why. Oh, I see why now. Let me switch it for you. I have to switch to the window. Now you guys should see a figure. Do we see a figure?
Yeah.
So the blue curve is the exact solution. That's that exponential function. And then the red dots are our approximated values. And you'll see that they start off very good. And as we move to the right, they become less accurate. But if I would shrink my step size, I would get my accuracy. So does anybody have a question about this? Comment, concern? This is something that's going to take time on your part to learn if you want to learn it. And that's what this first sort of assignment is really all about. It's one that's going to take some time for most of you. That's okay. That's, you know, remember, you do want to learn something, I think, right? You want to understand and you want to, these are the skills that are used in many places. I mean, Euler method is, you know, they made a big deal about that. I mean, that's one of the original, that's what they used in the, you know, in the moon landing. That's how they solved the equation, Euler's method. So it's something, it is a classical algorithm. It's also one of the easier ones to learn. It's not very sophisticated though, right? There's not, you know, and by the way, if you think about how this works, it's really just using tangent lines, which was something you learned about in Calc 1. It's using tangent lines to get approximations. So, does anybody have a question about this? Do you think you guys can do this on your own? If I share this code with you, again, you could go on Stack Exchange or anywhere. You're going to find other code of this. But it actually is not terribly difficult to do this on your own, you know. Now you would have to modify this code a couple places for each different problem. You know, you'd have to go up top. So let me show you what I mean by that. Do you guys see the code again, the editor?
Yep.
So you would have to change your capital F for each problem, and then you'd have to go down here and change your initial conditions for each problem. And then you would have to also change your exact solution. So there's 3 spots you would have to modify for each problem. But that said, this is something that, you know, I would hope you play around with. I would hope you ask questions. Someone once asked me when we did this class a couple summers ago, should I write a different file for each function? And I said, yeah, that's fine. You can do that. Or you can just modify this one for each problem. It's up to you. There's also, if you're real sophisticated, which I'm not saying you should be, but if you get real brave and real sophisticated, you can even write your own built-in function that if you go to the command line and you give it the equation, it can solve it for you. So that's even higher level stuff. If you know anything about function files, you might want to be brave and try that. I'm not saying you have to, but if if you want to see what you can teach yourself, there you go. Does anybody have a question about this? But once we get you guys figure this out, then we are good to go for starting the actual, what does this have to do with the neuron? Any questions? Comments? All right, well, if you guys don't have any questions or comments, I think we should stop and let you guys go work on it. And like I said, feel free to schedule Zoom meetings with me. I'd be happy to go over this stuff. I mean, I can look at your code. I can help you with the symbolic solutions. This is a tedious homework. It's going to take some time, but please try to, get it done so we can move on. I mean, that's the idea. So if you have any questions about particular problems, you just got to holler and let me know. All right?
All right.
Does anybody have any questions? Yeah.
Yeah, Dr. Grady, I would like to make an appointment with you on Wednesday after the class.
That's fine. How about, do me a favor, can you send me an email? So
Yeah, I can send you email.
Yeah, send me one right now, and then we'll start communication, and then we'll schedule something. All right?
Yes.
So do you want it after class or before class?
After class will be perfect.
All right, great. All right.